So I'm going to solve the same problem that you just saw on the previous slide by Ket's book. How many grams of oxygen do you make from 100 grams of water? So the first thing that I always do in my 5-step approach is, as always, you need to have a balanced chemical reaction equation. It's basically the recipe. So we're looking at decomposition of water. So we have water that is decomposing into hydrogen gas and oxygen gas. That's the skeleton equation. Before we can actually deal with this in terms of proportions, we have to balance it. We have 2 hydrogens on either side, so those are fine. We have 2 oxygens over here, so we need to have 2 oxygens over here. Balancing off the oxygens, we cause the hydrogens to no longer be balanced, so we then have to put a 2 there. Here's where things are a little bit different with the way I like to solve it. The next thing I like to do is I always like to extract the information from the problem and use my balanced equation as an organizational tool. So I take the given and the required information, what we're given and what we're asked to solve for, and I place it underneath the appropriate compound or element that it refers to, so I know where I'm starting and where I need to get to. Okay, so first thing it says, how many grams of oxygen? So that's obviously what we're asked to solve for. That's the required value. So underneath my oxygen, I'm going to put a question mark grams. I'm going to give myself the unit so I know what I have to convert to at the very end. And the question mark is just telling me that that is what I'm asked to solve for, or that's my required value. So how many grams of oxygen do you make from 100 decimal grams of water? And that decimal is important because that's telling us that that particular value has 3 significant figures. Without the decimal there, those zeros are ambiguous and we're not quite sure. When we put the decimal in there, it is telling us that that has been measured to 3 significant figures. So that's what I'm talking about in terms of listing the given the required information. And I'm going to use that balanced equation as my organizational tool. Okay, so that's my second thing I always like to do. Start with the balanced equation, list my given and requireds. Now, in terms of stoichiometry, we understand that the balanced equation is proportions of the elements and compounds that need to be reacting in terms of the actual numbers of particles. We have mass here. We need to then now convert to particles. Now, we're not going to go all the way to particles. We're going to go to these bundles of particles that we've talked about before, and we're going to convert these to moles. Moles is just simply an idea of how many particles of each we have. So in order to do that, we have to determine the molar mass. The molar masses that I've been using throughout all of these videos and all of the quizzes and whatnot is that online periodic table, just so that we have consistency. I find that it's a good one. It has more significant figures, has more decimal places, a little bit more precise. And that's why I use it. It doesn't change things a whole lot if you use the one in the textbook, but I have been using the one that is online. So when I calculate the molar mass of oxygen, I get 18.015 grams per mole. I'm going to list that underneath the water because that is the molar mass of water. I'm going to take those 2 values and I'm going to convert those to moles. Now, it's nice the way we've set it up here is to convert from moles, you're going to take mass and you're going to divide it by the molar mass. So when we list it in that way, it actually tells us the mathematical operation, or at least it helps us with this. I've done the calculation already, so it's 5.550929781 moles. Way too many significant figures, but in any intermediate calculation, I like to carry extra, and I only like to round off at the very end. Now, obviously, we can truncate this a bit, but we don't want to round off to the proper number of significant figures until we get to the very end. Okay, so that's the number of moles of water that we have in our 100 grams. We're going to use that value to now determine the amount of oxygen that is formed. Anytime we are comparing 2 different elements or compounds within the chemical reaction, we have to do mole proportions, or we're going to apply our mole ratio. So to go from water over to the oxygen, I need to apply a 2-to-1 ratio. Now, where did the 2-to-1 ratio come from? Well, in my balanced equation, 2 moles of water will only produce 1 mole of oxygen, so we have our 2-to-1 mole ratio. I'm going to show that mole calculation, or the molar mole ratio calculation, the way I've done it before. I'm looking at a water to oxygen ratio, which is a 2-to-1 ratio. Because we're working with equivalent ratios, the 5.550929781 moles goes in the first position of my ratio because that's referring to the amount of the amount of water. And I'm going to put an X in the second position because I don't know how much oxygen is going to be formed. As we've seen before, we're going to take your two inside terms, multiply them. Those are going to equal the two outside terms multiplied. So our 2x is equal to that 5.550929781. Divide both sides by 2, and we're going to get an x value equal to 2.77546489 moles of oxygen are going to be formed. So I'm going to bring that up here. So the number of moles of oxygen is at 2.77546489 moles. Once again, way too many significant figures, but we're going to deal with that in just a second. So we've gone from our water, we're now over to the oxygen. We know the number of moles of oxygen, but the question is asking for, remember we started with our target here, it's asking for what is the mass, or how many grams of oxygen, so we have to go from moles and convert to mass. To go from moles to mass, we need the molar mass, and because we're dealing with oxygen, we're going to use the molar mass of oxygen, which is 31.998 grams per mole. Moles multiplied by molar mass will give us mass. Here we divided, so here, to go the opposite way, we're going to do the opposite operation. So we're going to multiply those two, and we're going to get a value of 88.32555 grams. At this point, we now have to deal with our significant figures. Back to the original problem, there's our measured value. With that decimal, like I said, this is now telling us that we have 3 sig figs. In our question, our final answer has to have 1, 2, 3 sig figs. We're now going to look at the next value, and our final answer will be 88.8 grams of oxygen formed when dealing with proper numbers of significant figures.